So, hello everyone. So, we'll just wait for 5 minutes so that some more students can join. Then we'll start this live session. So, just wait for some time. Okay, so now we will be starting the session. So, let me first introduce myself. My name is Himanshi Singh. I am currently a PhD scholar at the Department of Mathematics, IIT Jodhpur, and I'm pursuing my PhD in broad area of probability and statistics. Okay, and I am your TA for the course Essentials of Data Science with R Software 2, Sampling Theory and Linear Regression Analysis, which is taught by Professor Shalabh from IIT Kanpur on the SWAM portal. Okay, so basically here we are discussing the content which has been discussed already in the lectures, and we will be like having some discussions about those content, and further we will see the practical application and the questions regarding those. So to have a better understanding about the topics. So basically, we are conducting the live. Basically, we are conducting the live sessions on every Monday. So this is the live session schedule. So here we are on the 8th live session. So it was basically scheduled for the 16th March, but we have postponed it due to some unforeseen circumstances to today. So it is now on like it's on Sunday, but the next session will be on Monday, that is tomorrow only. That is for the weekline lectures. However, for this session, we had postponed it to 22nd of March. So that is today. Okay, so this was about the postponement and all these things. And apart from this, these are the important Google the links. So first one is the Google Meet link, from where you can like get the access to this online meeting. And the second one is the YouTube link, which basically consists of all the recording of the live sessions. So this is the link to my channel where I'm uploading all the live sessions. Okay. And the third one is the Google Drive link. Basically, it consists of all the presentations and the R scripts which I'm discussing in the this live session. So I will be uploading those on this Google Drive, so you may access it from there. Okay. So our plan for all the live session is basically, so we basically follow that. I first of all give a brief recap about the topic which has been covered already in the previous week. Okay, so today we are doing that for 8th week. Okay, and then if there are some concepts which can be demonstrated in R, then we will be demonstrating them in R. Then further we will be focusing on practice examples. And finally, we will be discussing some of your doubts. If you have any, then we can discuss. Okay, so this was all about the class, the overview of the class. Further, we will be starting the discussion of the topics covered. So if anyone have any doubt regarding the overall idea about the sessions, then you can ask. Otherwise, we will start the topics. Okay, if there is no doubt, then we'll start the topic basically. So in the previous week, so in the week 7, we were basically discussed how to what basically in the what basically is happening in the bootstrap analysis. Okay, so we from so for example, if I have a data, from that data I'm again and again drawing a sample. Okay, and like for 5,000 of the times I'm drawing a sample, and based on those samples I'm calculating a particular statistics. Then I'm calculating the mean of it, which will give me the bootstrap estimate for a particular statistic. So that was basically happening when we were doing the bootstrap analysis, and we have discussed some of the practice examples for that also. Okay, now in this in now for this kind of lecture, we will be discussing about how this bootstrap analysis we can do using R. So we cannot do all these things manually. Okay, so for one or two replications we can do it manually, but if I want to have a more number of replications, like 1,000 number, to have a better output obviously, or to have a better estimate, then it is not possible to do it manually. Okay, so for that, first of all, we have to install the package, that is the package boot. Okay, so this command install.packages boot will you have to write it in R, and then you have to call the library. Okay, then there is a function called boot in this package, which basically returns the value of statistics which you want to calculate. So basically it gives you the bootstrap estimate. Actually, it gives you the bootstrap estimate, it gives you the bias, it also gives you the standard error. Okay, and it gives all these things for R number of replicates, which you can emphasize here. For R is equals to, you can emphasize here, you want to do 1,000 replications, you want to do 10,000 replications, whatever you want to do. Here you will be giving the statistics which you want to compute, and here you will be giving the data. Okay, so from that data, first of all, it will calculate the original statistics. Then from that data, it will basically take the samples. Okay, take multiple, say R number of samples, and for each of the sample it will calculate the statistics, and finally it will give you the statistics, the bootstrap statistics, and further it also gives you the bias and the standard error. Okay, now here there is a thing that how the statistic should be defined. So if I have a data vector, or I also have a data, I also can have a data in the form of data frame. Okay, so if I have a data frame, for example, then how this statistic should be defined. So this statistic should be function of data, okay, and function of indices. Okay, so here basically you have to define it in this form. So function of data comma indices. So in place of indices, I think I should write here actually I. Okay, so this is basically the indices, but because in the inside I'm defining this in the form of I, so that's why I have written it I here. Okay, so your function should be like this. So data and I, and here in inside this function you should give data I comma whatever. So it will basically take the data whatever the for different samples, you will have a different data. So if you construct a sample from the original data, that will be like data 1, then another data, another sample, that is data 2, data 3, data r. So we have r number of datas. Now for each r data we want to compute the statistics. So here we are returning the statistics. So this is in general I have written. I will be explaining this further by the help of the example also. Okay, here we will basically do some of the operation on this data, whatever the data is, and in order to find out the statistics. So if it is a ratio, for example, data has two rows. Oh, sorry. For example, data has two columns, and I want to find out the correlation between those two quantities. Then I will write here the function of correlation, and in the argument I will write the first column and the second column from the data. So that will be d dollar whatever the column name is, d dollar the first column comma d dollar the second column. In that way I will calculate the statistics and return it. So it will be then calculated for each of the sample, and further the boot will calculate the overall estimate for the bootstrap estimate for the statistics, and also it will calculate the bias and the standard error. Okay, so this is about the boot package. Okay, now further, if I want to further directly, so it will give you a multiple kind of information, and it will so if I just run this command, it will not give you the the bootstrap statistics. In fact, it will give you the original statistic, the original value of the statistics, that is for the original data, but not the bootstrap statistics directly. So for bootstrap statistics we have to write, so we'll just store this the command in result, and I will write the mean of result $t. So if I write this, then it will give me the bootstrap estimate. And also if I write this, it will give me the bias. And if I write stand SD of result $t, then it will give me the bootstrap error. Okay. So this is about the bootstrap analysis by using R. So through R, you can directly calculate the bootstrap estimate using the boot command. Okay, so this was a kind of a point estimation. This is a kind of a point estimator. So basically, if I have a statistic and I want to find out the estimate using the bootstrap analysis, then I'm just finding out a particular value or a particular estimate, a particular bootstrap estimate. So this was all about the point estimation. So now what about the confidence interval? So if I want to find out the confidence interval for such statistics, then what should be the methodology, and further how can we implement this using the R? So there is a methodology, and how can we use R in doing that thing? So we will not always be doing the things manually. So how R is useful, and what are the commands in R we can use to find out the confidence interval, bootstrap confidence interval, and what is basically the theoretical aspect. So first of all, if I say about the theoretical point of view, so there are 5 ways by which bootstrap confidence interval can be calculated, and so the some of the methods have like advantage over the other. So for example, if I consider one kind of a method, so this method may be useful for a particular type of a data. Okay, if for a particular, if a data has a particular characteristics, for example symmetric, then normal approximation, the based bootstrap confidence interval will be better apart from others. But if it is not symmetric, then other method is maybe valid. Okay, so there are in broad five kind of bootstrap confidence interval, uh, five types of methods to construct bootstrap confidence interval. Okay, so that is bootstrap confidence interval, which is based on the normal approximation. Okay, basic bootstrap confidence interval based on percentile. Okay, and it is bootstrap confidence interval based on T method, and bias corrected and accelerated confidence interval. Okay, so these are the five type of methods by which we can construct a bootstrap confidence interval. Okay, now let me explain it a little further. So for example, if I want to construct a bootstrap confidence interval or based on normal approximation. Okay, so what basically it do? So for example, first of all, let me take it here that okay, this T is my original sample. Okay, so original data, for example, if this is my original data. Okay, fine. So from this original data, I will collect some sample. So let T1 star be the sample, T2 star be the sample. And for example, I'm taking TR star. So these are the R samples I'm taking. Okay, now, for example, I want to compute a statistic confidence interval for a statistic T. Okay, so let me name it as T naught. Okay, original data. Now statistic, if I compute by using this data, that will become T naught. Okay, so basically here I'm computing this statistic T naught by using this data T naught. This is a data. So this is a like x1, x2, xn, like n length of data. Okay, now so I've calculated the statistics for this data. Now I will again calculate the statistics for this T1 star. So this is T2 star. So I've calculated the statistics for all our datas, our bootstrap samples. Okay. Now how I can do the normal approximation? So the 100 into 1 minus alpha % confidence interval for this method will be what? So it will be this T naught minus Z alpha by 1 minus alpha by 2, not that alpha by 2 only. So it is Z alpha by 2 into under root of VB, comma T naught plus Z alpha by 2 under root of VB. So now what VB is? So VB is nothing, under root VB is nothing but standard error of bootstrap estimates. So these were the so this I should not say the bootstrap estimate actually. So I can write it as a standard error of, so if I write it as a T1 star till TR star. Okay, so that is basically T1 star summation of TI star minus the mean of these divided by the whole square, and it is divided by n minus 1 or r minus 1 because there are r number of values we have. Okay, so this is basically the standard error of this vector, which can be calculated. So if you calculate the first, second, third, and rth bootstrap, the value of the statistics for them, then just write VAR of these values and it will give you the standard error. Okay, so this is basically the root VB. So this is the normal approximation where we are assuming that the rate of the statistics, basically, so the distribution of the statistics can be normalized. So that basically we are approximating using the normal approximation. Okay, now what about the basic bootstrap confidence interval? So 100 into 1 minus alpha % confidence interval using the basic bootstrap interval is twice of this T naught, so this T naught only, this T naught, sorry, the statistics, minus T star 1 minus alpha by 2, or I should write it as a tau, okay, because T is like, it is becoming same. So let me write it as tau star 1 minus alpha by 2, comma 2 T naught plus, sorry, minus tau star alpha by 2. Okay, so this one. Okay, so it is not so let me take another page actually. Okay, so it will be, what? It is 2 T twice of T naught minus tau star 1 minus alpha by 2, comma 2 of T naught minus tau star alpha by 2. Now what this tau star alpha by 2 and 1 minus alpha by 2 is? So for example, I have this statistic, the statistics computed on the sample, so that is T1 star, T2 star. So these are basically the numbers I'm getting for each of these sample TR star. So this tau star is basically the 1 minus alpha by 2th quantile, okay, of this data. Okay, and this T star alpha by 2 is nothing but alpha by 2th quantile of this. So we can, if I'm using R, then we can basically find out using quantile function. So it is quantile function for this. So if I consider it as a vector T, okay, and then this will be T comma 1 minus alpha by 2 and quantile T comma alpha by 2. So it basically gives us the point before which there are 1 minus alpha by 2 entries are there. Okay, and this will give us the point where before this point, this point, there are alpha by 2 number of entries. Okay, so this is about the basic bootstrap confidence interval. Now further, if I want to find out the confidence interval based on percentile, so this is 100 into 1 minus alpha percent confidence interval, which is based on percentile. So it is given as tau star alpha by 2 comma tau star 1 minus alpha by 2, where this tau star is same as this one. Okay, so this is the alpha by 2th quantile, and this is the 1 minus alpha by 2th quantile. Fine. Now, when I want to calculate using the T method, so this is a little different and a little tricky. So for example, if I have this, we have evaluated the statistics T1 star, T2 star till TR star. Okay, and we had the sample T1, T2, TR. So these were sample. This is the value of the statistics at those sample. Okay. Now, further, we will calculate the standard error at each of the sample. So that is SE1 star, SE2 star. For each sample, we will calculate SER star. Okay. For each sample, we will calculate this. Fine. And so here the T naught was the original data. So T naught will be the value of the statistics at the original this one, and let standard error be the standard error of original data. Fine. Then what we will do, we will find out here Z star. Okay, so that is Z1 star, Z2 star, ZR star, where ZI star is nothing. So ZI star is nothing but TI star minus, TI star minus T naught divided by SEI star. Okay, so for each of it, we will calculate the ZI stars. Okay, then further what we will do, we will find out the 100 into, so 100. Okay, so let me do it. So 100 into, so here, so 100 into 1 minus alpha percent confidence interval, okay, based on T. So it will be what? So it will be T naught minus Z star 1 minus alpha by 2 into the SE naught. Okay, comma T naught minus Z star alpha by 2 SE naught. Now what here this Z star alpha by 2 and Z star 1 minus alpha by 2. So these basically are quintiles of this Z, Z1 star, Z2 star, ZR star, Z1 star, ZR star, this one. Okay, so this is the way by which we will calculate and SE naught is basically the standard error from the original. T naught is the statistics, the value of the statistics for the original data. Okay, so this was about the student, the bootstrap confidence interval based on T method. Okay, now bias corrected and accelerated confidence interval can also be constructed. I will just give you the code because the mathematics behind this is a little tricky and it is a little lengthy. So that's why I'm not considering that here. Okay, so we'll get this kind of a confidence interval by using directly the R code. We are not going in the mathematics. Okay. Further, now if I want to further use find out these kind of a confidence interval using R, then directly I can use this command boot.ci. If I want to find out the confidence interval based on normal approximation, based on basic this the second one, the basic bootstrap confidence interval. Okay, and also the confidence interval based on the bias corrected and accelerated and based on percentile, all those four methods. Apart from the T method, apart from this T method, other four methods can be we can get the confidence interval with respect to those methods by using directly this command boot.ci. Now how this command works, so boot.ci will write, and the argument we'll just write what this basically result is. So the result is the values or the output we are getting from the boot command. So first of all, we will use the boot command over our data, and for a particular statistics we will evaluate that, and we'll just place the output of that boot command here in the boot.out. Okay, and in the type we will just put norm basic p percentile. For percentile it is PRC, and BCA for the this corrected and correlated, the accelerated basis bias corrected and accelerated confidence interval. So we'll put BCA there. So this will give us um, the confidence interval. Okay. Now, if you want to find out the particular, like 95%, 97%, 93%, for that, in the argument we can write PERC and equals to, will give the percentile which we want to calculate. Sorry, the confidence. So not that. So I have considered that here in the examples also. So here you only have to write, I think, CONF to be equals to. So let me show it to you here. Yeah, so if you want to find out the 95% 95% confidence interval, then you just write CONF is equals to 0.95, and 93 and other percentage confidence interval, then write just 0. Like 95 for 95% is 0.95, and CONF is equals to 0.95, 0.93, and for the others you can do it similarly. Okay, so let me just add it here also. So this is, I don't know what is the problem with this. You can just specify here what percentage you want, what how much percentage confidence interval you want. Okay, now further, for student distribution, if you want to do, so for that this command BOOT is used to find the confidence interval for, and the so it will basically give us the confidence interval for the data vector and the required statistics. But for this we have to install a package. Okay, so for this package, for this particular function, if you want to use, you have to install this package bootstrap, and then you can give the command BOOT x comma theta is equals to statistics. So here basically, if x is a data vector, then you just give that data vector here, and in place of the theta is equals to statistics, in the statistics you just give the whatever statistics you want to require, you want to like calculate. So for example, if you want, if you have a data vector and you want to calculate the mean, so just give BOOT here the data vector, and here the mean of that data vector. So for example, here if it is x and some values is already assigned here to x, then just give here in the place of statistics mean of x. Then it will give you the confidence interval. Okay, but if it is a data frame, then you have to specify the statistics in this way. So first of all, you have to specify the statistics as a function of x and the data. Okay, and then in the command BOOT, you have to specify at first place, you have to write 1 till n. So basically, if this is a data frame, for example, if your data is in a data frame and it has, for example, many number of rows, for example 15 number of rows, so you have to give it here 15 because you want to evaluate for each row. You have to consider all 15 rows, that's why. So if you want to consider less number of rows, then you can specify whatever n you want, how many rows you want to do the analysis on, then on that thing you have to specify here. Okay, and in place of theta you have to give this statistics, and here the statistics should be defined as a function of x and a function of data. So I will be explaining this through an example also. And here also, if you are making this statistics as a function of x data, then you have to specify the data here, X data to be the data frame, whatever the data frame you want to consider. And you want how many applications, you have to specify here as NPOOT as 500. And if you want to do more number of applications, then you can just specify here. Okay, so it will give you the confidence interval. So further, I will be discussing all these commands in the questions also. But if anyone have any doubt regarding this, then you can ask here. Okay, so if there is no doubt, then we will go with the questions. So let us see the questions here. Okay, now the question one says that for a given data, so this is the data is given. We want to write a boot function to estimate the bootstrap mean. Okay, and the bootstrap standard error and bias. So first of all, the statistics is that I want to estimate mean. Okay, so bootstrap mean we want to estimate. So the statistic here is mean of X. Okay, so now if I want to write a boot function for it, so first of all, what I will be writing, I will be so for this I will be writing boot, and at the first place I will give the data. So let X is, so X is assigned, so I will just write X here. Okay, then I have to give the statistics, what the statistics I want to evaluate basically. Okay, so I will write here, for example, stat. Okay, and the statistics I have given. Now further, what I have to give here in this, then further how many replications I want to do, that I have to give. So R is equals to, for example, if I want 500 applications. Okay, and what basically the stats is, so stat is mean of X. Okay, so here you can see, here I have done this. So basically, first of all, I have installed the package. So I have installed the package. Okay, then here I cannot directly, actually here in the stat I have to write it with indices actually. Okay, so here let us see. So here I have given this data vector the value X. Then I have written the function of statistics. So that is function of data comma indices. Okay, so that is mean data. So I want the mean function to be mean, and data here, the data is here, and I want to have it in the square bracket. I will write indices. Okay, then I will pass this function, the stat function, in this boot function. Okay, so here I have to write with this mean of X I want, but I also have to write mean of X, and in this I have to write I actually, or indices, whatever you want to make it as a. So basically what I will do, so let me write it again. So here I will make this stat as a function. So it is as a function of, for example, I have this to be a function of data comma indices, and in place of this I can also write d and I. It is just a merely a variable. Okay, and here I will write mean of data, and in the square bracket I will write indices. Okay, so the same thing. And in place of data indices, if I write d and I, then I can here also write d and I. Okay, now here I'm not passing the data, I'm passing this function here in stat, in the boot function, and here I am giving the data actually. Okay, so in this way I will so let us see that what the output is. So if I see the output here, so this is the output basically. So here it is showing that original, so basically 8.6 is coming as a, so because this is the original statistic. So if I so this is the original data. Okay, if I find out mean of this data, original data, that is x. So this is basically coming out to be same because this is the original value of the statistics at the original data. Okay, then here the bias is given, standard error is given. Nowhere it is given like what is the bootstrap estimate. Now, in order to get the bootstrap estimate, I have to write RES $1 T. So that is basically these are the bootstrap estimates for each of the replication. Now, how I can get the bootstrap final bootstrap estimate? So that is the mean of RES $1 T. So basically we take the mean to find out. So that is 8.5894. Okay, so this is the bootstrap estimate, and uh, this is the original, and difference of both of them is the bias. Okay, and this is the bias, and these are the values at each sample. So if I calculate the variance of, or the standard error, the square root of the variance of this vector, then I will get this. So let me show you that also. If I calculate the square root of variance of this data vector, that is RES $1 T. So it is giving me 1.088, and you can see here it is also 1.088. So this is nothing but the standard error for these bootstrap. But at particular sample, what is the basically the estimate, and I want to calculate the standard error of those estimates. This is basically the standard error. So this is a kind of a vector by through which we can find out the standard error. Okay, so these are the codes for this only. So I have asked for bootstrap mean, I have asked for bootstrap standard error, I have asked for boot bias. So for those, the codes I have written here. So this is for the original mean. So that is RES $1 T naught. Okay, so it will give you 8.6, that is the original mean. The bootstrap estimate is given by mean of RES $1 T, so that is 8.5894. Now for the standard for the standard error, I have to write ST of RES $1 T. So that is this 1.088. So in place of ST, so here I have written directly the SD, but here I have written square root of a variance. So both are the same thing. There is no difference. This is the direct function. Here I have taken a little longer function. Fine. And for the bias, so for the bias, we just subtract the bootstrap estimate, the original mean from the bootstrap estimate. So this is that. So this is the bias. So that is coming out to be minus 0.0106. So here also it was same. So that is the same, minus 0.016106. Okay, so this was about this question. Now in place of this function, now if I have a single data vector, I can do only I will just change the function here. This in place of mean, if I want sum, if I want median, if I want whatever I want, I will just perform the calculation using this data and the square bracket indices. I have to perform all the calculation over this data and the square bracket indices. Okay, so if I consider a next question, so here it is asking that using the same data on Q1, estimate the median. So what I will do, only the change will be, so basically the change will be, first of all, if I want to define the function of statistics, so that will be function of, let me define it like function of d comma I. Now here, what I want median. So it is median. So this is a direct function in R. Median of d and the square bracket I will write I. Okay, so this function will give me this, and now further I will write boot. At the first place I will give the data, so that is x. Then I will give the function, that is stat, the statistics function, and R is equals to, for example, 1000, 500, 100, whatever you want to give. So the same thing I have done here also. So here you can see, so here I have named this function as a different name, data comma indices and median of data and indices, and I've done the same thing, and I have stored the result in res2. And you can see here, if I find out res2, so this is basically this is the original, this is the median of the original data, so which we can see by writing median. The original data was x only, so that is 9, that is same. Bias is coming out to be minus 0.384, and the standard error this. So bootstrap estimate will be mean of res2 $t. So that is coming out to be 8.616. And if I take the difference of 9 and 8.616, the bias is this only. Okay, and the ST of res2 $t, so this will basically give us the bootstrap standard error, that is coming out to be 1.683264. Okay, so this was a like a similar kind of a question. So for this we have done this, and for the standard error I will just write ST of, so if I for example, if I stored it in res2, then ST of res2 $t. Okay, so it will give me that. Okay, now in the next question we have the question on data frame. So in place of a data vector, what if we have a data frame and if I want to find out the bootstrap estimate? Okay, now here in the question it is asked that this is the data frame of income and expense. Okay, and I want to find out the bootstrap estimate for the statistics, that is a mean of the income divided by mean of the expense. So basically I want to find out the mean of this, and I want to find out the ratio. This is my statistic. So then I want to find out a bootstrap estimate for this statistic. Okay, and also I want to find out the corresponding standard error for the estimate. So before doing anything else, first of all, let us define as the statistics function. So what will be it? What it will be? So it will basically be a function of data and indices, no doubt. Okay. Now how we will be defining this function? So it will be the so here it will be a function of d comma I. Okay. Now, so D is basically the data frame. So here the data will be data frame. Okay. So it will be D comma I. So here what I'm doing. So this is what. So uh this is first index, second index, third index. So means this is the first row, second row. So it is basically the index of the data. Okay, so this is this is basically consist of different like rows. So first data, second data, third data, it will basically make sure that. So we will write it in this way: d of I comma the nothing in the second argument. Okay, and What I want mean of income and mean of expense. Fine. So means the first row. I want the first row, the mean of first row and the mean of second row. Sorry, not row, column. The mean of first column, mean of second column, and I want to divide it. So this is my statistic. Okay. So basically what we will be doing, so we have just stored this value in, for example, D2. Okay. Now, so here in D2, the data is stored. Now what I will be finding out, D2 is basically a data frame. So D2 dollar income, okay, divided by D2 dollar expense. Fine. So this is my statistics now. So I want to return this. Fine. Okay, sorry, not D2 dollar. So I want to evaluate mean also, na. So D2 dollar income will give me the whole column. I want to find the mean, of course. So I will write here. Let me write it again only. So that is return mean of D2 dollar income by mean of D2 dollar expense. Fine. So this is now my statistics. Now further what I want to do, just I will use the command boot, and the first I will give the data frame. So let us consider that I have stored these values in the data frame df. So df comma this is stat, and if I want to give r is equals to r, and if we will not give, then it will perform it by default. So this is the function. I've constructed the data frame here df. So let me show that to you first of all. So here you can see there are two columns, income and expense. Okay, then I have constructed this stat function, so which is a function of data and indices, and here I've stored the value of that in d variable. Okay, so here also I've stored it in d2 variable, and here this d and d are same, and indices here. And yeah, so basically this and this should be they should be performing the same thing, but we can also change. In place of data I can write x, in place of integer I can write y, but here I have to specify then x and in the bracket y, and here this is d only, and I can also change this, so it is, these are just variable. Okay, and here I want to return this mean of d dollar income and mean of d dollar expense, and then I'm basically finding out the bootstrap estimate. So let me show you that what is the outcome coming. So RES 3. So original is coming out to be 1.923, bias is this, and standard is this. So I want to find out the bootstrap estimate. So it is coming out to be 1.9243 here by the mean of REC $3 T. So they will give me the bootstrap estimate, and this SD command will give me the bootstrap standard error. So this is already given here also. Okay. So I can find out for the data frame also in this way. Only the difference is how to make this the function which is basically specifying the statistics you want to calculate. So this is different. The difference lies if you are considering the data frame, and if you are considering data vector, the difference lies in defining this function only. Okay, so let us move for the fourth question. So in this question, it is asked that plot the histogram and QQ plot for the bootstrap estimates obtained in question 1 and question 3. So first of all, I want to plot the histogram and QQ plot for the bootstrap estimates. So here we have obtained the bootstrap estimate. So this is basically, finally it is giving me this bootstrap estimate, that is 1.924371. But for each sample, we got some bootstrap estimates. For each sample, I got particular value of these statistics. For other, I got so that this vector which I got. So there were thousand of the values. I want to plot histogram for these values. Okay, so I want to plot histogram for these values. So these are the value. So for the first sample, the mean was coming like this. For the second, the mean was this. For third, for the mean is this. For fourth, the mean is this. Okay, so these are for a particular bootstrap sample. This is the value of the statistics. For a different sample, this is the value of the statistics. So these are those values. And if I want to plot these values, I want to plot the histogram of all these values, and I want to see that how the distribution of this is basically having, what is the distribution for this data. So if I'm getting an estimate, I'm getting many estimates, now if I, so basically I have a data now. So what is the distribution of that data? This is this distribution have a similar characteristics like normal distribution, or it is different? Okay, so for that, this plot command basically is used to plot the histograms as well as the QQ plot. So let me show you. So the first the results from the first question, where we were finding out the bootstrap estimate for the mean for a particular data. So there we have stored the result as res1, this vector. So if I want to plot this, so you can see this is basically the histogram here, and this is the QQ plot. So QQ plot is representing that how our distribution is fitting to the normal. So the line, the line which is the dashed line is the plot for the student, sorry, the normal distribution, and these are, this is the plot for our data. So it is basically lying on this line only. So this basically shows that our data matches with very much match with this normal distribution. At the ends, you can see that there is like missing values here, which basically does not happen for the normal distribution. So you can see that these points are also a little different from this line. However, in the middle, it is behaving like a the normal distribution. Okay, so this will give us the histogram. This is for the first question. Now, what about the third question if I want to plot? So here also you can see that it is also performing kind of unlike the normal distribution, apart from the extreme values like these values. So there is a little different from this line. However, in the middle it is performing like in normal. The distribution is like a normal distribution. Okay, so basically the distribution is kind of asymmetric. Okay. Further, it is asked in the question. So here, this is a question. So yeah, so we'll use basically the command plot. Okay. So what was that the result was stored in the variable. What was the variable? res1. So yeah, res1 and plot res3. Okay. So this was the result from question 1, and this is the result from question 3. Fine. Now, further using our compute 95% bootstrap confidence interval based on normal basic percentile PCA. So for this, we have already discussed that we have the command. What command? What command we used for computing the confidence interval? That is boot.ci. So that is boot.ci and boot.out. So here I will give the data which is coming, so the result which is coming from the question 1, so that is res1. Okay, because I want to do all the things for the first question. So the result, so the result which I'm getting from the boot command, I will just write it here. Okay, comma, I want to compute 95% confidence interval, so I will write PERC to be 0.95. Okay, and I want to calculate it for normal basic percentile BCA, so I will write type is equals to C NORM norm basic PERC and PCA. So this will give me the confidence interval. So let me show this. So here I have written. Okay, so not PERC actually. Here you should add CONF. So PERC I think for the B double O double T. Okay, so it is CONF. Sorry. Yeah. So if I run this, so you may think you may see that these are the intervals. So this is for the normal approximation, this is for the basic one, this is for the percentile one, and this is for the PCA. We are getting different confidence interval. Okay. Similarly, for the next one, it is asked that also for the data. I want to also for the data and statistics which is given in question 3. I want to compute the 93% bootstrap confidence interval. Okay, so for 93% bootstrap confidence interval, we just have to make the change. For third question, we have stored the result in RES3, so I've just written it here. And this is same as this, and the CONF to be 0.93. So if I run it, so you can see here we are getting the 93% confidence interval. Okay. So yeah, so this was about this question. Yeah. So if there is any doubt, then you may ask. Okay, so then we will discuss next question. So I want you people to just see this question a little bit and then just think about that what we can do for this. Just give me a minute. Yeah, so just see this question and just tell me that what we can do. So basically, here in the question, it is written that consider the given data frame. Further, so we want to consider this data frame where we have two columns, basically X and Y with some values. Okay, and here I want to find the bootstrap estimate of the ratio of the sum of the columns. So I want to find out the bootstrap estimate for the ratio of the sum of the columns, and further I want to compute the bias, and then finally I want to construct 97% bootstrap confidence interval based on percentile method. Okay, so first of all, here I've included everything. So at first I want to find out the bootstrap estimate, then I want to compute the bias, and finally I want to find out the confidence interval, which is based on the percentile method. Okay, so first of all, let me write that what is the statistics basically. So if this is x1, x2, xn, x 1, 2, 3, 4, 5, 6. So there are 6 observations. So if this is xi's, then the I want to estimate the ratio of the sum of the columns. Actually, not columns, column values. Okay, so let me it is summation I going from 1 to 6. Okay, so basically what it is, 20 plus 30 plus all this till 70 divided by 12 plus 14. So this is the statistic. Okay, or we can also find out using sum of x if x is this vector divided by sum of y if y is this vector. Okay, so what I will do for bootstrap estimate, so this is basically a data frame. So first of all, I will I will write the statistics. What is the statistics? Okay, statistics function. So if I want to write stat, so I will write as a function of data and indices. Fine. And here I will store the value in D2. So what is D2? T comma I. Fine. And what I want to do with this data? Okay, so D2 will be obviously a data frame. Fine. So D2 $x, I want to do sum of D2 $x means the first column divided by sum of D2 $y. I want to return this. Fine. So this is basically the statistics. Further, in order to find out the estimate, we will write boot and the data I will give here. So for example, if I consider store this data in df, so df comma this is stat, and then we are done. R to be, for example, 1000. Okay, so let me show this to you in R also. So this is the data frame I've constructed, and if you see it, so it is df. Here, this is the data frame. Constructed this function based on data and indices. Okay, sum of D$x, sum of D$y, because I've stored it here in D. Okay, then I've just used the boot function. This is a similar way in the previous one. So we can see here if I run it. So this is the original statistics. The bias we got as minus 0.010255, standard error is 0.135. So what is the bootstrap estimate? So bootstrap estimate is coming from mean of RES $5 T. So that is 2.22115. Okay. So here we have stored this result as RES 5. Okay. So the mean of RES $5 T will give us the bootstrap estimate. Okay, and bias, how can bias be given? So mean of this RES $5 T minus RES $5 T naught. So it will give you the bias. Okay, so here also it is written mean of RES $5 T minus RES 5. So that is obviously the same as this minus 0.010. Okay, now what is the confidence interval? So in the confidence interval, basically I will just pass this boot. So in confidence interval, for the confidence interval, not write it like this. So confidence interval, I just pass boot dot ci. Okay, and in the data here, boot dot ci data here. Okay, not the data. I have to just pass the value which is coming from the boot command. So that is res 5. Further, what was in the question? 97% bootstrap confidence interval based on percentile method. So 97% confidence interval I want, so I will write CONF to be 0.97. And percentile method I want, so it is type is equals to, for example, so I will write PRC only. So that will give me the confidence interval. Okay, so this is 1.9612 to 2.520. Fine. So this is about the. Well, so here we have discussed the bootstrap estimate also, and the wait. Yeah. So here we have find out using this, and here in R also we can find out. So here if I run this all these commands, then I get from here I got this is the bootstrap estimate, this is the bias, okay, and this is the confidence interval. Okay. So this was about this question where we have included every like confidence interval estimation also and the point estimation also using the bootstrap technique. Further, let us now here before we have only considered the methods to be other than the studentized bootstrap confidence interval. Okay, so if I want to find out the 95% studentized confidence interval, then what I have to do? For that, I have to install the package Bootstrap. Okay, then then there is a function called BOOT in that package. Now we will be using that package in order to find out the confidence interval. Okay, now for here in the question it is asked that for data in question 1, I want to compute the 95% studentized confidence interval for mean. Okay, so first of all our statistic is mean. I want to compute the mean. Okay, I have to use the function BOOT. Okay, at first I want to give the data. So I will give the data so that X was stored, X was there in the question 1. Okay, so BOOT, the data I have given, then I have to give the statistics. So that is mean of X. And we are done. Okay, so let me show this to you in R. Okay, so I have to make it as a function of X. So I have to make this as theta. So theta to be function of X. Okay, and that is mean of X. So that is only the function of data. No indices are here. Okay, mean of X. Now I will write X comma theta. And I want 95 95% confidence interval. So here I will write PERC to be 0.95. Okay. So here you can see that first of all, let me install the package. So it is available here and I want to call the library then. Okay. Then I stored the data and then I have created the function of the statistics and then I have used the BOOT and last I have written $CONF points. So it will only give me the confidence point actually. So it is RES6. So if I write this here, so it has given me the 95% confidence interval. Okay, so for 95% confidence interval, we have to specify here PERC to be. Okay, so here PERC to be not 0.95 actually. So it should be C 0.025 comma 0.975. So how it is coming? So actually if I have, so here alpha I have to be 0.05. Okay, so alpha by 2 is 0.025 and 1 minus alpha by 2 is 0.0975, not 0.975. So if I want 95% confidence interval, then I have to write it here 0.025. So because this confidence point are for alpha by 2 and 1 minus alpha by 2. Okay, so that's why if I do not write this, for example, if I do not write these specified confidence points, then let me show you how the output will be. So if I do not write this, and I also do not write this confidence point, I only write this, then if I see RES6, so it is giving me many other information also. So here it is 0.001, 0.01 for these points also, the value is coming, okay, for the confidence in order to construct the confidence interval. But I want 95% confidence interval, so I want the lower limit to be the 0.025 and the upper to be 0.975, this one. So my confidence interval here will be 3.749, comma 12.689. Okay, so which by the previous command it was coming like this only. Actually, it is coming different. because if I run it twice, then the bootstrap samples may differ. So that's why the confidence interval may differ. So it is coming different. Here it was 0. For 0.025, it was 3.749, but here it is 5.096. So the difference is coming because of because we are uh, doing the sampling again. And if we do the sampling again, the samples may be different, and we can get the different confidence intervals. Okay. So if you want to reconstruct again the same similar kind of result, then you have to use this set.seed commands in order to get the same results again. Okay, fine. So this is the thing for the data vector. And if I want to do it for a data frame, for example, so the next question is like for the data in question 3, using our computer 90% studentized confidence interval. So basically it is a data frame. In question 3, we have considered an income and expense data frame. Okay, so for that, if I want to find out the confidence interval, then how my function of statistics will be looking like. So if I want to do that, so let me construct this stat function. So that is a function of, so I have to function of x comma x data. Okay, so here I want to make it as a function of this, and I want a correlation between income and expense. So first of all, I want correlation between, so x data is the data actually. So x data, it is a data frame. We'll give the data frame here. Okay, x data. Okay, and the x data x comma 1. Okay, and x data, because at first in the previous boot technique also we have written indices at the first. So x data x comma 2, this one, and I want the correlation between them. So this is the command for correlation. Okay, so this will give me the statistics. So here also we have done the same thing. Yeah, but I've written it in a different way, but this is also fine. Okay, and now further, if I use the command b double o double t, okay, at first I will give 1 till the number of rows in the data. So I will write just n row x data, comma. Then further I will give the statistics, so that is stat. Then further I will give the data. Okay, so x data is equals to, okay, so so for example, let us consider that we have stored the data in df. So df consists of the data. Okay, so data in question 3. Okay, so x data to be df. If I write this, then I'll get the output. So here in the df I have stored the income and expense, but in place of x data I have only written here df. From df only I have done the things, but if you write it in this way also, you will get the output. Okay, so there is like no difference, because these are only the variables. So then here this theta is used. Theta is a function of this, and here theta is used. So in place of theta, if you want another name, you can give d1 name, for example, and here write this theta is equals to d1. So there is no problem. Okay, so here you have to write actually theta is equals to stat. Okay, that is important. Fine. So in this way, I want 90% confidence interval. So 90% confidence interval means alpha is 0.10, means alpha by 2 is 0.05, and 1 minus alpha by 2 is 0.95. So I have to give here PERC to be equals to C 0.05 comma 0.95. Okay, dollar CONF points. Fine. So here I have done the same thing. Okay, here I have given the 0.05, 0.95, and if I run it, RES 7. You can see that this is the confidence interval. Okay, so this is for this T method. Okay, so here we have constructed the 90% confidence interval for the studentized method, for or I can say the T method, where we are using uh, the different statistics, the different approximation other than the normal, basic, and those the four methods which we are using for the boot command. Here we are using the function b double o double t. Okay. Okay, so further, if these things are fine, then I will be discussing one manual example. So here till now I was also only discussing the examples which are based on R commands. Okay, so the studentized method was a little different, a little tricky. So I want to discuss one manual example for that in order to get the idea that how this studentized method is working in order to construct confidence interval. Okay, so this is the question basically. So for the data in the bootstrap sample, I want to compute the 95% studentized confidence interval for mean. Okay, so here it is given that data is given, that is 2, 4, 6. So we have data of length 3, and that is 2, 4, and 6. From that data, 3 bootstrap samples are considered here. So that is first one is 224, second one is 466, and third one is 266. Okay, now I want to calculate the 95% studentized confidence interval for mean. So basically mean is my statistic. Okay, so my statistics T will be what? Mean of the data. So now so I want only the manual calculation basically. So if I want the mean of this data, so this is the original data. So mean will be what? 6, 4, 10, 12 by 3. So that will be 4 for this data. And what will be the standard error? So standard error for statistics T. Okay, so that is the standard error of, so what is the mean of data? So what is basically it is x bar. Okay, so if the data is x1, x2, xn, so the statistics basically is x bar, and I want to find out the standard error, that standard error. Okay, so what is it? So in fact, in place of standard error, let us first write the variance only, because that the standard error will be the square root of the variance only. So the standard error will be, so our variance will be, so variance of x bar will be what? 1 upon n square variance of xi. Okay, so now the variance of 1 upon n square variance of xi will be what? The standard error will be what? The square root. So that is the variance of xi divided by n. Now since we do not know the whole sample, so we may not know the whole variance, but we can estimate it using the sample variance. Okay, so it will be s by, okay, so this is n times also. So wait a minute. So because it is summation of 1 upon n times summation of xi, so it will be n divided by n square. Okay, so it will be n, so it will become root. So it is s by root n. Now how s can be calculated? So this is VAR of data. So it is basically 1 upon n summation xi minus x bar whole square, n minus 1 here from this. So that is basically 1 upon n is 3, that is 2, 1 upon n minus 1 is 2, and it is 2 minus 4 whole square plus 4 minus 4 whole square plus 6 minus 4 whole square. So this is 2 minus 4 whole square is 2. This is 0. This is again 2, which is 4. 4 plus 4, 8, and this is 4. So the standard error is also coming out to be. So this is 2 minus 4, that is 2 square, that is 4. Plus this is 0. 6 minus 4 is 2 square, that is 4. 4 or 4, 8 divided by 2. This is again 4. Okay. So we have done this in here also. So this is standard error is not 4 actually. So this is standard error will be 4. So the standard error was s by root n. So this is s actually by root n is root 3. So 4 by root 3. So here I have coded this. So if I want to find out, so this is the data, this is the mean, this is the standard error. Okay. So if I find out, so here the standard error is coming out to be 1.1547. So this is 1.1547. Okay, 4 by root 3. So by other way also, if I want to like 4 by root 3, if I find out, so that will be same only. 4 by SQRT of 3. Okay, sorry. So this is not 4 actually. So this the so this s is, this is square root of this one. This s is square root of this. Okay. So this will be the square root. So this will be 2 here. 2 by root 3. Okay. So 2 by root 3 will be the. So yeah, it is coming like same 1.1547. So it is 2 by root 3. Fine. And now further, same things I want to do with the sample. Okay. So basically this is in the previous setup, if I want to do, then this is T naught actually, and this data is T, and the value of the statistics is T naught, so that is coming out to be 4. This is T1 star. So this mean will be T1 star, T2 star, T3 star. For each of them, we will find out the standard errors, and for each of them, we will find out the Z star. So that Z star is nothing but we have basically used that the Z star is nothing but the T star minus Ti star. Okay, so this is basically the mean. So the Ti star minus of T naught. So this is this 4 divided by the Se star. So that is this. Okay. Okay, so let me write star here just for understanding. Okay, so this is Z star. So what is the mean of this? 4 and 4, 8 divided by 3. So here I have written for the sample 1. So the mean, standard error, and Z I have written here. So these are coming from the same formulas as before. So the mean one is 2.66. So it is 2.66. So let me write it here only. So this is, for example, mean, so which I am considering to be this is mean, which I'm considering to be Ti star, and the second one is standard error, it is SEI star, and this is Z star, which is equals to TI star minus T naught divided by SEI star. So what the values I'm getting? So it was 2.66. Okay, and the standard error 0.66 for the first sample I'm considering. And what was that one? That is -2. Okay, so this we can use it manually. So this all thing will happen directly by using boot.ci, but here I'm doing it manually in order to further show you that how the things are happening. Now for the second sample, let us do the same thing. Okay, so it is mean 1, mean 2, so that is 5.33, SE2, so it is 2. Okay, and now let us do for sample 3. 4.66, getting standard error 1.33, statistic 0.5. Fine, so this we got. Now we will find out the quantile from this. Okay, so let us store this value in Z. So for example, Z is -2, 2, comma 0.5. Okay, now we will just find out quantile of Z comma 1 minus alpha by 2. Okay, and quantile of Z comma alpha by 2 in order to find out the small alpha 1 Z alpha by 2, this is star, and Z alpha by 2, this is star. Okay, this is this one and this is this one. So this we will be finding out using the quantile function actually. So we just store these value in Z. We take alpha to be 0.05 and just ZL and ZU are calculated, and we will further put these values in the confidence interval. So what will be the confidence interval now? The confidence interval will be T naught, okay, minus Z star 1 minus alpha by 2 into SE. Now this standard error is nothing but this one, this SE 1.1547. Okay, SE I can say comma T naught minus Z star alpha by 2 SE. Okay, so the same thing I've done. ZU, which is the Z of 1 minus alpha by 2, and ZL, which is Z of 1 alpha by 2, and this will be the lower confidence point. So that is CIL, and upper confidence CIU. So let me show what the values are coming. CIL. So it is 777, sorry, 1.777,201. So this is 1 point. So this is coming out 1.777, comma, it is CIU 6.165. So it is approximately this confidence interval. So this is 95% confidence interval. Okay, so this was about the questions, and if anyone has any doubt, then you may ask. Okay, and I hope the things are clear to you. And if not, then you may ask if there is some doubt. And also, apart from this, the recording for today's session I will be uploading on YouTube. The presentations and R scripts I will be adding on Google Drive. And the next session will be on, that is for week 9. So that will be tomorrow. Okay. And it is from 6 to 8 p.m. only. Okay. So yeah, if anyone have any doubt, then you may ask. So basically today we have discussed about like how to compute the confidence interval, bootstrap confidence interval based on 5 different approximation methods. And apart from this, we also calculated the bootstrap estimates using R. So the methodology for bootstrap estimates, how to calculate the bootstrap estimate was given before in the uh, previous discussion, but in today's discussion we have discussed about how to do all those things using R, how to compute them using the R codes. Further, we considered the bootstrap confidence interval for the 5 different type of methods. We have discussed the methodology, what is the mathematics working behind it, what is the statistics working behind it, and further we have seen that how in R we can find out using different functions, different packages, how can we find out the bootstrap confidence interval based on these 5 types of methods. Okay, so and also we have considered the studentized confidence interval for a manual calculation in order to understand the mathematics or the statistics behind it in a more clear way, that basically what behind the coding, what is happening actually. Okay, so so the methodologies for all of the approximation methods are different. So yeah, so I think now this bootstrapping, sampling techniques, these the concept, the methods are, these are covered. Now further from the next session, we will be discussing. We will start discussing about the linear regression analysis. So what basically linear regression analysis means? How can we understand it mathematically, and how can we implement R in it? So basically, how can we use R in order to find out the estimates when we are considering the problem of linear regression analysis? Because this estimation is coming everywhere, wherever you are going. If you are going towards a linear regression analysis, you want to estimate, you have to estimate that what are the like parameters, what are the scalars which are there present, and on all those methods we will be doing estimation, like point estimation and the confidence interval estimation for those scenarios also. So we will be starting the linear regression analysis from the next lecture. Okay, so yeah, if there is no doubt, then we will end this session. And if there is something you may ask, you may also post that on this NPTEL portal, where there is a Q&A section. You can post your question, and someone will answer your question. If you have any query or anything regarding any concept or regarding any um, rule regulation or anything, you may ask there also, and you may ask here also. The floor is open. Okay, so if there is no doubt, then we will end this meeting. Okay, thank you for joining, and let's meet tomorrow uh, for the discussion for the next week lectures. That is week 9 lectures. We will be discussing there. We'll be discussing the basic concepts of linear regression analysis tomorrow from 6 to 8 p.m. So let's meet tomorrow, and thank you for joining. And we will be ending this meeting now.